Here is another example where you can see that the alkyl group is attached to the benzene ring. Now, if we subject the same compound towards oxidation in the presence of either KMnO4 or sodium dichromate and water, you can see that there's a formation of the carboxyl group. I mean, the whole group has been removed and the carbon attached to the directly to the ring has been oxidized to the carboxyl group. So irrespective of the length of this alkyl group, it has to change into the carboxyl group. So this is called the oxidation of the alkyl benzene. So you can try on such kind of the compounds. You will see in the later on in different cases where how the alkyl group is being see that oxidized. The same kind of the product could result irrespective of the type of the alkyl group it attached to the so you can make a practice of these two compounds that which of the product could be obtained from oxidation of these see in this slide. So for the hydrogenation of the aromatic ring, you need to have a very high amount of the pressure. If we subject the same compound to the same reaction to a very high, like the 2000 psi pressure, then we will be able to reduce the ring as well to change it into a cyclohexane type ring, and then along with a double bond. But under the normal conditions, only the outside double bond will be hydrogenated. So this is regioselectivity. So today we will be continuing with some more example about the regioselectivity. I already told you that regioselectivity is the one where you have more than one site in the reactant for the attack, and the attack is going to happen at only one position favorably. Then we say that the compound contains the regiocenters, and this reaction can be called then as the regioselective reaction. Sorry. So let's take an example where you have a double bond and you have the aromatic ring. If we are subjecting this compound to the reduction, then how to reduce the double bond while keeping the aromatic ring as such. If we are only intended to reduce only the double bond and keeping the double bond which is present as a substituent to the aromatic ring, and keeping the aromatic ring as such, we need to have some of the selective reducing agent that can only be capable of reducing the outside double bond and keeping the aromatic ring as such. So one such example is the one is called the hydrogenation of the compound called the 4-phenyl-3-butene 2-on. So this is a compound where it can be reduced with the hydrogen and palladium in presence of ethanol. So if we try the hydrogen and palladium in the presence of ethanol under the normal condition of temperature, we can reduce the outside bond. There will be no reaction at the aromatic ring. So there will be no reduction for the aromatic ring, but the outside double bond will be hydrogenated. This is selectivity. Why I'm saying that it's this selective reaction, because it was possible that the ring, the aromaticity would also have been lost, but it doesn't happen. Why? Because this palladium is selective for the under the in presence of ethanol solvent under the normal condition of temperature. It's a selective for the outside double bond. It will nothing to do with the. It will not do anything to the aromatic ring. So you can see in the slide that the 1,2-dimethyl benzene has been subjected to the hydrogenation, but this time you can see that a 2000 psi pressure has been applied along with the hydrogen and platinum as a catalyst at 25 degrees centigrade. You can see that the benzene ring has been reduced, hydrogenated. This is, again, you can see the other compound, 4-tetrabutylphenol phenol, where you can see that the rhodium catalyst has been tried at 1 atmosphere at 25 degrees centigrade. A rhodium carbon coupled. This is a type of the catalyst. Now, if you use this catalyst, even at 1 atmosphere, it will be capable to reduce the benzene slide. We have a task, and the task is that you can see that we need to produce the N-propyl benzene from the benzene. Now you have to produce the N-propyl benzene from benzene. This is the task. So what kind of route you will be following? For instance, if you want to do the alkylation reaction, just by doing the just by subjecting the benzene ring, reacting the benzene ring with the N-propyl chloride, so the reaction can be called as the Friedel-Crofts alkylation. So there is no problem. There will be a formation of the N-propyl ring will be replacing the hydrogen, and we have the N-propyl benzene. But along with this product, there will be another product. So we will be getting a mixture of product, because this N-propyl benzene, it will be rearranging into the more stable carbocation. So there will be a hydrogen hydride transfer. So by having this reactions, we will be getting two products, right? You can see there in the slide that one the isopropyl benzene, and the other one is the N-propyl benzene. So if we are intended to have the N-propyl benzene, along with that we will be getting a mixture of the product. But if you want to 100% only one product, how to do that? What are the other possible ways or way where we can have only a single predominant product? Avoid the rearrangement reactions and avoid the selectivity and to have the 100% stereospecificity, you need to use the propanol chloride. Propanol chloride will be allowed to react with the benzene ring. So if you use the propanol chloride, it will be doing the acylation reaction first, and once you get this acylated product, then you will be able to reduce that acylated product with the hydrogen and the palladium, and ultimately you will be getting the propyl benzene. Now this is the 100% product. There will be no side product in this reaction. So you can see that in the first case we got a mixture of two products, but here in this case we got only one product, that is the 100% product. So in this reaction there is no side products. Here is another task, and the task is to synthesize this para-bromo benzoic acid starting from the benzene ring. So how to do that? Now there are two ways that we can do that. Firstly, let's suppose if we subject the benzene ring to the alkylation and we bring the methyl group, and then thereafter we, this is one way, and then subjecting that to the halogenation, bringing that para-bromo toluene, and then oxidizing that methyl group by the KMNO4. This is one way we can. The other way is to subject the benzene ring to the halogenations in presence of the Lewis acid as a catalyst, and then thereafter changing the benzene ring to the bromobenzene, and then thereafter we subject the bromobenzene to the Friedel-Crofts alkylation, and then we will be getting this para-bromo toluene, and then thereafter oxidizing the product, we will be getting the para-bromo benzoic acid. So here you can see that both of the routes, they are feasible. Is there any problem with anything, with any route? If you have here, you have no problem. You can follow any of the route in order to reach the final product. You can use or choose any route, any way to reach that product. So here we have the task, the real task. Here you can tell me the product, the reactant, the suitable reactant, and the in fact the whole reactions which can give us this product. Have you any to reach this product? If I start with the benzene ring, and then if I start with the nitration first, then what will be the problem? So if I start with the nitration first, subjecting the benzene ring towards nitration, we will have this nitro group, right? Nitration reaction, you already know that you need to have the nitric acid as well as the sulfuric acid that will give us this nitrobenzene. And then thereafter, in order to reach this final product, the next step I can do is to subject either the nitrobenzene towards alkylation or halogenation. Now my question is that will this give this product if I subject the nitrobenzene to the Friedel-Crofts alkylations, keeping in mind that nitro group is a meta-directing. So if it is meta-directing, how to get this ortho alkyl benzene? Because this alkyl group is, we can see in the slide, is at ortho positions to the nitro group, while it is at meta positions to the chloride group. So if I subject the nitrobenzene to the alkylation, it will not give me this product. So there is a problem. So it means that I cannot start with the nitration first. Let's suppose I am starting with the Friedel-Crofts alkylation first. So if I subject the benzene ring to the Friedel-Crofts alkylation, then again, I will have two mixture of that product. One will be the N-propyl benzene, and the other will be isopropyl benzene, right? So doesn't seem a suitable reactant. So if I subject the benzene ring, right? If I subject the benzene ring to the acylation reaction, right? Trying the propenyl chloride, subjecting the benzene ring to the acylation first, then I will be getting the acyl propenyl benzene. I will be getting that ketonic product, right? So, and then thereafter, if I reduce that, I'll be getting this 100% product of alkyl benzene, N-propyl benzene. Now this N-propyl benzene has been obtained. Now what could be the next reaction on it? Will this next reaction will be nitration or the halogenation? So if I subject this N-alkyl benzene to the nitration, then of course I will be getting this nitro group, right? I will be getting this nitro group at the ortho positions to the alkyl substituent. But my point is, after that I have to subject this nitro-alkyl benzene towards the, I have to subject this to the halogenations in order to bring the chlorine group on that ring, on the benzene ring. Now, do you think that it will be possible? Because you can see that this alkyl group is orthopara directing. So how it will allow the chlorine ring to come on the meta position? On the other side, you can see that the nitro group, this nitro group is meta directing, and how it will allow the chlorine to come on the para positions to the nitro group, because this nitro group, it's meta directing. It will never allow to come and never allow the chloride atom to come on the para position. So there's a problem. Now, without looking at the next slide, just look at this and solve this problem over here. So if instead of that, why don't I after having this alkyl benzene, why shouldn't I subject this benzene ring to the after the nitration? In fact, after getting the alkyl benzene, then I subject it to the nitration and then to the reduction. If I get the aniline group, then aniline can, an NH2 group can easily direct the coming electrophile Cl group at the para position, right? So you can see that our target is to reach at 4-chloro 1-nitro 2-propyl benzene. So we can start either with the para-chloro nitropenzene, and then we can also start with the ortho nitro propyl benzene. So these are the two options we have, but whether we can start with the para-chloro nitrobenzene, the answer for this is that if we start with this, we will not arrive, we will never be arrived at the 4-chloro 1-nitro 2-propyl benzene. The reason for this is that the nitro group at one side, it is the very first point that we should keep in mind is that this ring is highly deactivating group. So why it is highly deactivating group? The nitro group is attached to the ring that makes the ring highly deactivating. On the other side, we can see that the chlorine group somehow though it can donate the lone pair of electron, but still it has also some sort of the electronegativity, and we can see that there's a pulling effect, I mean withdrawing effect of the electron. It has the capability. So if these two things are collectively, they are present at the same time, this will make the ring highly deactivating. So under that conditions, you can't expect the electrophilic substitution reactions at either positions. So except for under a special conditions, you give some special conditions, then maybe it is possible. But now at this conditions, it would not be possible uh, for the electrophilic substitution reactions to happen. Starting with the 4-chloronitrobenzene, because the coming group has to come that will be ortho to the nitro group, because this is the required product. So if we subject this 4-chloronitrobenzene or para-chloronitrobenzene to the chlorination in presence of the Lewis acid, the first thing that we can expect is that the first thing it would not react, whether because if we forget about the deactivation of the ring, even though this reaction doesn't seem feasible, because the required product requires the propyl group to be on the ortho positions to the nitro group. So if we place this on the ortho position to the nitro group, it means that that will be matter to the chloro group. So matter to the chloro group means we are going against the trend, because chlorine is the ortho para directing. On the other side, nitro is the matter directing group, right? So it can't happens this way. Just look at the other side where the ortho nitro propyl benzene. Now the reactions, you can see here that if we in the required product, I mean the 4-chloro 1-nitro 2-propyl benzene, the chlorine group is at 4 position, or at the para positions to the nitro group, and to the meta position to the propyl group. So if you know that propyl group, which is an alkyl group, is a ortho para directing, right? And nitro group on the other side is the meta directing. So it means that if we are to place the chlorine group at para positions to the nitro group, then this nitro group will become meta to the alkyl group, which is quite unusual for the current trend, because favorably nitro group cannot afford the coming electrophile to be ortho or para to it, right? And on the other side, you can see that alkyl group on the also have some concern that it cannot afford any coming electrophile to be on the meta positions to it, right? So this will not give us the correct isomer. That's why this reaction will also be not feasible. But what about if we are starting this reaction, if we are starting with metachloropropyl benzene? So now this metachloropropyl benzene, you can see that if it is subjected to the nitration now, if it is subjected to the nitration, the nitro group definitely will come at the ortho positions to the alkyl group. So on placing this on the ortho positions, you can see that this nitro group is now para to the chloro group, chloride group, as well as it will be ortho to the and propyl group. So by subjecting this this reactant, we will be arriving at our product, that is the 4 chloro 1 nitro propyl benzene. You can see that this is the most feasible reactant that we can start with to reach the final product. But your question would be that there is one other ortho positions available, that is because you can see on either side of the alkyl group there are left right there are two available positions for the, so we can't place the coming electrophile on the other side of on the other ortho positions to the alkyl group, because at you can see that on either side of alkyl group there are two ortho positions available, but only one of the ortho position is feasible, that makes the electrophile para to the chlorobenzene, not the other one, right? If we place it on the other side, you can see that that will become uh, too much crowded, is it? So this crowded nature will not allow, will not be feasible. So rather than placing it on the first side, again you can see that if we are about to prepare the metachloropropyl benzene, starting with the benzene, what we can do. So this is very simple. You can, first of all, you can start. So what will be the possibility of doing this? You can start with the acylation reaction rather than first, and then bringing the chlorination, and then thereafter following by the reduction, we can reach to the metachloropropyl benzene. If you are starting with the alkylation, then of course chlorine cannot become on the meta position, right? It can't come on the meta positions, because if you start with the alkylation first, alkyl group is the ortho para directing. So for bringing the chlorine on the meta position, first of all you need to subject the benzene ring to the Friedel-Crafts acylation, and then thereafter, if having this is acylic group, and then thereafter you will be able to subject this propiophenone to the chlorination in presence of the Lewis acid, that will give you the meta metachloro propiophenone. So then thereafter you can subject that metachloropropionone to the selective reduction. Now this is called the selective reduction in presence of the palladium carbon couple. This reduction will only be able to reduce the carbonyl group rather than reducing the aromatic ring, because for the reduction of the aromatic ring you need to have some around a very high pressure of 2000 psi, but we are not giving that much pressure, and we are giving only providing the simple conditions where a palladium carbon couple is used in presence of the ethanol. So you will be arriving at the reduction of the carbonyl group and will be changing it to the metachloropropyl. So this is the mechanism for that. So here are some problems for your practice. You can practice on it and then get back to me in the due course. Once you are done, you can share your uh, ideas how to bring about the formation of the required shared with you few slides that you can make practice on, and then come back to get back to me once you are done, or if you have any problem with in doing that, just make a practice on it, uh, and then back to me if there's problem. I think it's a very healthy practice for you, because so far whatever we have read about the electrophilic substitution reactions, I don't think now you will have any problem in suggesting the type of the reagent or the route, proper route for the synthesis of all these reactions. But you need to look for the feasible route that will be, satisfying all the conditions, keeping in view the basic principles that the electrophilic substitution reactions are based on. So I think you will be able to do that. Um,
A. Hey, this is how you can search my channel. Type knowledge plus understanding in the search box. Then wait. Then. Hey, this is my YouTube channel knowledge plus understanding. Then you can click on the subscribe button and also don't forget to click the bell icon. Thank you.